Hello, calculus fans! So we've done the work to compute the area of a parametric surface. Now we want to do a specific case where our surface is defined by an equation, z equals f of xy. And this is actually a fairly common case where we want to compute a surface area. Let's go ahead and assume that f has continuous first partial derivatives, as is the case with any sort of nice function that we'll run into in this class. And for this surface, we're just going to simply use x and y as our parameters. That means here's a parameterization of the surface. X is just x, y is just y, and z is f of xy. So that's the function that's defining the surface. If you like, you can write this in vector form. You can say r of xy is equal to x, y, f of xy. All right, then let's follow the plan that we had for parametric surfaces. We'll compute Rx cross Ry, and then we'll get the general formula for the area of a graph. So Rx is equal to 1, 0, df by dx, whatever f happens to be, and then Ry is 0, 1, df by dy. And if we were to cross these, and you should verify this, we'll get negative df dx, negative df dy, 1. Don't take my word for it. Compute a cross product. It won't take you very long. And then if we compute the length of this vector, we'll get the square root of df by dx squared plus df by dy squared plus 1. Notice that the minus signs disappear because we're squaring something. Okay, so here's a general formula for the surface area of a surface that's given to us as a graph, as z equals f of xy. And I think it is worth pointing out that this formula is analogous to the arc length formula that we learned in freshman calculus. That formula looks like this. It's the length of a curve is equal to the integral from a to b of the square root of 1 plus f prime of x squared dx. You should note the similarities. What's the main difference? Well, there's a double integral instead of a single integral, and there's two different derivatives. Before we just had one derivative, now we have two different partial derivatives. But otherwise it's really the same thing, and so there's an analogy here that computing surface areas for functions of two variables is analogous to computing the length of a curve. Okay, that's all for now.